Okay, so good afternoon, everyone, and welcome to the special colloquium at ICTS. So it's a great pleasure to have Professor Andy Ruina giving this colloquium. So he is professor of mechanical engineering at Cornell University, and currently he's a visiting professor at the Indian Institute of Science. Professor Ruina works in the areas of friction, and dynamics and mechanics and robotics, biomechanics and so on. And he looks at very interesting and very difficult problems like how bicycles work and how people walk, and also I think how to make robots work. He's in fact made a robot which I think walked like 65 kilometers or something. He has a wide range of interests. I just learned that he is actually interested in the three-body problem, which is a very difficult and interesting problem. And he has a quite an amazing algorithm which actually gives you a whole class of periodic orbits. Okay, so this is something really interesting. And so I think Professor Ruina will be in Bangalore for quite some time. He might be here for a very long time. And I hope people will get to interact with him at in ISC. Okay, so Andy, you can start.
Okay, thank you for the introduction. It was 80% correct, I think. So let me say two introductory things. First is that I think the talk I'm giving is kind of fun and people might have questions. So I'll try to end at about 4 o'clock, and then people leave who want to leave, and then I'll stay and answer questions or talk about it as long as people like, so long as we're not kicked out of the room. Second is, I'm in India for a long time, I think. I'm going away for May, June, July, but I'll be back in August, and then I'll be here September, October, November, December, January, for years. So I'm available if you want to talk to me, ask me questions, or tell me things at ISC, and there's a bus that goes back and forth, I found out recently. So I'm happy to talk to people about anything. Right now, I have a job, and my job title, the only responsibility I have is talking to people. So you're welcome to take advantage of that, or try to. Okay, so this is not really an academic talk. It's a pedagogical talk or entertaining talk, something like that. I've thought about writing a paper about this stuff, but I have not done it, and I probably never will do it. So the title is Experiments in a Falling Cat Go Sour. The big word in this talk is non-holonomic, and I will try to explain what that word is, and then talk about locomotion, and the whole thing is kind of stories. Okay, so it starts out, my training was not in dynamics or in robotics. My training was in solid mechanics, stress and strain, elasticity, and things like that. And then I was a professor. And about 1984, when I was 30 years old or so, and I was not in dynamics at all, this guy named Tom Kane came from Stanford and gave a lecture at Cornell, and he was introducing Kane's equations. And as an advertisement for Kane's equations, so that's really good. Really good. Thanks. As an advertisement for Kane's equations, he gave a puzzle problem to the audience, which I'm going to give to you. And so the talk will be a little game here, and I'll give you puzzle problems, and then you're not allowed to answer. If you know the answer somehow, you're not allowed to answer, right? You have to be based on thinking. So the problem he gave, which he was going to solve with Kane's equations, is well, you have a car, and you have a choice between braking the front wheels and rear wheels. And you want to know which is the better thing to do, which is the better thing to do. So let me make the puzzle more clear. Imagine that your car has two brake pedals. One of them locks the rear wheels, and the front wheels roll smoothly. And the other one locks the front wheels, and the rear wheels roll smoothly. And you're going fast in your car, and you're going to slam on the brakes so that either the front wheels are locked or the rear wheels are locked. And perhaps the car was going straight, but maybe 1 degree or something off straight, and you're not going to steer it from that point on. And the question is, which one is directionally stable or unstable? Or are they both? Is there any difference in terms of, will the car go haywire or tend to be straight afterwards? Okay, so that's the puzzle. You can lock the rear wheels, or you can lock the front wheels. And which one? You're not worried about the car tipping over. You're wondering, does it keep going straight? Okay, so car going down the road. I'm tangled up in this. front wheels, rear wheels. You can screech these wheels and these ones roll, screech these wheels and these ones roll. Maybe the car is 1 degree tipped, and then you keep going like this and it comes to a stop. But as it comes to a stop, does it tend to straighten out or does it tend to get more crooked? One way or the other. So we want it to go straight. We don't, which of these things is better? So that was the puzzle problem he gave. So I give you that puzzle problem. So first of all, does anybody know this puzzle? They've seen this puzzle before. Okay, does anybody know the answer to this puzzle? You've seen it before, because you see my video, you know it somehow. Okay.
Turns out my generation of Indians
Yes.
watched Audi car ad on TV. So my generation of Indians watched an Audi car ad on TV, which answers this question. That is why I know the answer.
Okay. So in America, there's where I come from. There's a different class of people who know the answer, which is the secret society, which is this is a society of people that's so secret that people don't know the other members of the society, and the secret society is the people who go to grocery store parking lots at 2 in the morning after a snowstorm. So it's really great fun to drive your car around a big flat area in the snow. So if you go at 3 in the morning to one of the big Wegmans Tops parking lots, there'll be 3 or 4 cars doing skidding experiments, and you don't know who the other ones are inside the car. You just see them there. So those people know the answer to this puzzle. Now, the reason they know the answer is because on a real car, when you step on the pedal brakes, it primarily brakes the front wheels. And if you pull the emergency brake, it primarily brakes the rear wheels. So you can actually do this experiment. Okay, so he gave this puzzle to the audience. And I was sitting there, and even though I don't know any dynamics, I was like a 3rd grader. I know, because I did know. And the reason I knew is because a few years earlier, I had a pickup truck, and it was a very icy day, and everything was very slick. And for reasons I do not know, I wondered what would happen if I skidded the rear wheels on my pickup truck, which in that case was an old handle like this. You pull out this handle, go, and there's this ratchet. And I did this skidding experiment in my truck. It was a 63 Ford F100 pickup truck. I don't really know why I did it, but the result of the experiment was this. So I had my seatbelt on. That's not me, that's my neighbor. He came in to rescue me. I was hanging by my seatbelt in there. So how did I do that is I brake the rear wheels. Okay, now, I didn't ask you what you thought your opinions were about this question. I didn't collect the opinions, I probably should have. But I know that most people think braking the rear wheels is the stabilizing thing. And it's exactly the wrong answer. Okay, so I won't take a poll. Later on, I'll take polls on some of these questions. Okay, so why does it happen? So if you look at a car, I'm going to have the car going this direction to your right. And we have rolling wheels here, and we have skidding wheels here, or the other way around. Let's just say we put the skidding wheels in the back. So the car is going like this, and it gets a little off kilter here. So it's going like this. We get a friction force in that direction from this skidding wheel. And the lever arm of that friction force is just this little distance here. You have these rolling wheels up here. The rolling wheels are capable of having a full friction force only perpendicular to the wheel. Like you think, what is the job of a wheel of a car? Part of it is to make it roll easily forwards, but part of it is to keep the car on the road. What keeps it on the road is that sideways force. So a car is rolling on the road. How hard do you have to push it sideways before it skids? Is the full frictional coefficient. So we have potentially the same force here with this big lever arm. So what happens, it gets a little off kilter, this wins. This drag force, which you thought, most of you, in your, because I read you, I'm a mind reader, thought that this is like a parachute holding this back. But that only gives a very little stabilization compared to this big lever arm of this instability. So you do the backwards of that, put a wheels back here and the drag here, it gets a little cocked. This drag gives this little lever arm to destabilize it, but this rolling force has the full friction force with this big lever arm, and that pulls it back in. Now, to make it more clear, which is the way that Tom Kane did, as he cheated, and let's just say, actually the friction's not important. Let's just say we can put wheels on the back and a frictionless pad in the front, or the other way around. Well, if you have wheels in the back and a frictionless pad in the front, it's the same as an arrow flying through the air. So a feather cuts through the air and only moves in the direction of the feather, the same way a wheel rolls on the ground and only goes in the direction that's pointed. And so a car that's braked on the front, if you just ignore the friction, is like an arrow going through the air. So an expression straight as an arrow, that's an expression is born from the stability of arrows because they have a wheel in the back, feathers, wings, sails, whatever, something that cuts one way and doesn't go the other way, which straightens it out as it moves. Whereas if I put the feathers in the front, shoot an arrow backwards, it gets a little off kilter and it immediately pops around crazy. Okay, so he wanted to advertise his equations as a good way to show this. You can write the equations and you get the result. What it says here is just to show the difference is if you want to think of this as an arrow, imagine there are feathers in the back and a ping pong ball in the front, which has exactly the same area as the feathers. So the feathers in the back have this anisotropic friction. They have big friction this way, small friction this way. The ping pong ball has equal friction in all directions. And the anisotropic one wins because it gets this big lever arm. This ping pong ball has this small lever arm in the front. So it likes to line up, even if you put a ping pong ball in the front of the arrow, which is like the car skidding. Okay, so how do you go about dealing with this with equations? I'm not going to show you Kane's equations, but here is a car, and we're looking down on the car, and here are the real wheels. Well, just to make it simple, just put one real wheel in the middle. Don't worry about this car tipping over. We're just worried about its directionality, so it's a very low, flat car. And this thing is going to be sliding on ice. The only friction is going to be the resistance to sideways motion of this wheel or this ice skate here. So this is called a Chaplygin sleigh. Some Russian guy named Chaplygin studied this in the 1890s or something like that. Okay, so this is a mechanics problem. It's got this wheel constraint here. The wheel constraint is that the wheel can go in this direction and it can't go in that direction. So that's if we look at the velocity vector of this wheel and dot it with a normal vector perpendicular to the line of this car, then we get 0. So what is the velocity of point C? It's the x dot, y dot. Those are the two components. This normal has a minus sine theta, cosine theta. Those are the two components of this vector in terms of these base vectors. So this is the constraint equation. Okay, this is called a non-holonomic constraint. And the word holonomic means whole, as far as I know. So it's a not whole constraint. And what that means is a non-whole constraint is this is an expression involving derivatives that you can't integrate. So what do you mean you can't integrate it? Is you can't find a function of this form equals 0. That when you take the derivative of it gives you this. Now I once gave a lecture actually at a meeting called Non-Holonomic Mechanics where I said that. And one guy in the meeting said, well, you can't do it, but maybe Ramanujan could. And he didn't mean to be telling a joke, but that's a joke because Ramanujan can't either. It's like, it's not that I'm not smart enough to, it's that it can't be done, right? This is what they call a non-integrable constraint. What would be an integrable constraint? If I said x dot equals 0, that's the same as x equals a constant. I take the derivative of this, I get x dot equals 0. There's no expression involving x, y, and theta that when you differentiate it get this. Now, how can I know that that's true without doing any math? Here's my car. It has a skate in the back. So it's sliding on the plane. The plate is the blackboard. And it can only go this direction. It can rotate about this point, and it can go the direction my hand is lined up here. That's what the wheels do on a car. That's what a skate does. Now, if it was true that there was some function of x, y, and theta that was a constant, it would mean that this thing is stuck and can't achieve all possible values of x, y, and theta while respecting this constraint. But look at this thing. It can certainly go that direction. It can certainly go that direction. It can certainly go that direction. So it can get every value of x and y. But it can't move this way. But what if I want to move that way? Well, I can turn the wheel this way, go up like this, turn back, and go like this. So I can move directly sideways. I can get this to any x, y, and theta on the plane, which means there's no restriction of no function of x, y, and theta equals a constant that can be honored. So that I can parallel park means that you can get to things that are in a direction that you can't go. Okay, so that's what non-holonomic mechanics is about. It's about restrictions on the velocities that cannot be not expressed in terms of restrictions on the configuration. Okay. Now my advanced slide features stopped working. Please move forward to the next slide. Don't do that. Hide, start again, see if that works. Come on, next slide, next slide, next slide, next slide. Is there a right arrow button here somewhere? View. Navigator. Okay, worst case is I go here. Okay, so here's an experiment that, shows the result. I forget whether grocery carts in India have casters in the rear wheels or not. I think they have casters in the rear wheels, don't they? Four-wheel casters. Okay, well, American grocery carts have casters in the front and no casters in the back. And what does a caster mean? Is that this is point of contact is slightly behind a vertical axis here that has a good bearing. So whichever direction this goes, this wheel drags behind. So this wheel functions differently than a car wheel. It's free to move this direction. And if you try to move it perpendicular, it aligns to that direction. So it's free to go that direction. So the net effect of a caster wheel, things like this on the bottom of chairs, if they're well lubricated and they work well, is that they make this as if it's a frictionless pad. Whereas these wheels go straight and they're like a single wheel in the middle. So this is very close to the Chaplin sleigh or to a car with rolling rear wheels and frictionless pads in the front wheel. So just to show how the caster works, it allows motion freely in any direction, whereas the back wheels can go front and back, but they can't go sideways. And you see it's very stable going frontwards with the rolling wheels in the back and effectively the skidding wheels in the front. But if you try to make it go backwards, it's unstable and then pops around to going straight. So it's more parking lot experiments. I have no idea why my navigator stopped working. Okay, so a similar thing goes with bicycles. Bicycles have this non-holonomic constraint feature. When I first started talking about this, which was a long time ago, there was a community of people in physics, which I guess this would include people like you, who didn't like the result of this calculation. Because what happens is you do this calculation and you find out that going forwards is exponentially stable. That if you disturb this thing, the disturbances die exponentially in time. But this system is a conservative system. There's no energy dissipation anyplace. There's no forces doing positive work or negative work anywhere in this system, because the force here on this skate is perpendicular to the velocity. So there's a theorem that people think in mechanics that says conservative systems can never be asymptotically stable. And here's a conservative system that is asymptotically stable. Well, the theorem, people remember it wrong, is the theorem for holonomic mechanical systems. And this is a non-holonomic system. It's got this funny constraint in it, and the theorem doesn't apply. So this is an interesting thing about these kinds of systems that have these kinds of constraints, these non-holonomic constraints. Okay, now what are examples of non-holonomic constraints? Another joke from Tadashi Tokieda. He said a good subject has a few theorems and many examples. And non-holonomic dynamics has a few examples and many theorems. So the subject of non-holonomic dynamics is the subject of skates and wheels and balls rolling. Okay, so it turns out those are the only examples. So it's a big theory about those examples. Well, in that set of examples is also a bicycle. And there's various people in the past 130 years or so have tried to write equations of motion for bicycle. We did a really thorough job of it. So there's a very common model, which you think of bicycles, 4 rigid objects, 2 wheels and 2 frames, a rear frame and a front frame. You assume perfect rolling with no sliding. You assume round wheels, you assume a bearing with no friction. A thing to study with these is just how the bicycle rolls without any control whatsoever. If you take the equations and linearize them, you get something of this form, where Q is a vector of two terms. One is the steering angle, and one is the lean angle of the bicycle. And then the other coordinates, like the angle on the plane and the X and Y coordinates in the plane, are what are called ignorable. You don't need to include them. You can get a closed set of equations with just the lean and the steer. You take these equations, you assume that there's no torques on the bicycle except for gravity. And you try to study what goes on. And various people have done this over the, as I said, the past 120 years, about 30, and about 3 of them have done it correctly. They're very complicated equations. Nowadays with computer algebra, people can get them more reliably correct. Okay, so what happens if you linearize these equations about straight ahead rolling? You get that this is a plot, which is eigenvalue on the vertical axis and speed. And each curve is a different eigenvalue. The dark curves are the real parts, and the dotted curve is the imaginary part. For stability, you'd like all the dark curves to have real parts less than 0. And there's a little range of speeds where the model says you get this asymptotic stability of the bicycle. So let me show you that. Here's a bicycle, supposedly. The file contains some media that's not compatible with QuickTime Player. The versions change here. Maybe this one is compatible. Okay, here's a slow motion video. So this is a bicycle that's been pushed. And what happens is when it leans left, it steers left. When it leans right, it steers right, and it balances itself. The more global view of this thing maybe will work if I try this. Maybe not. Oh, there we go. So bicycle can balance itself. It's asymptotically stable. It's exponentially stable. The realistic model, which is pretty accurate, has no energy dissipation. So this violates the theorem that says conservative systems can't be stable. The theorem is a non-theorem. It doesn't apply to non-holonomic systems. Okay, any questions about bicycles, non-holonomic mechanics? I'm going to change completely to angular momentum, or change 80% to angular momentum. Any question about what I said so far? Who here knew that bicycles can balance themselves? Raise your hand if you knew that. Raise your hand if you didn't know that. Okay. Now, why or how do they balance themselves? It's kind of a puzzle. There are 2 theories that have been sort of popular for about 100 years. One is that it's a gyroscopic effect, something about the front wheel acting as a gyroscope. Another is that the front wheel is kind of a caster, like a grocery cart. And then if you look at the axis of steering, it hits the ground a little in front of the contact point. And so the front wheel drags behind the axis, like the caster wheel on a shopping cart drags behind. And that makes the wheel go straight, and that balances. And we wrote a paper, which took lots of years of work, but to show that you can make a bicycle self-stable without either of those effects. So not that those are not part of the equations, but they're not necessary conditions, neither necessary nor sufficient for making a bicycle balance. Okay, so now I'm going to change gears a little bit. I guess I can show you this. You change the operating system, and then everything falls apart. Okay, so here's a bicycles made with my colleague in Netherlands. This has 0 gyroscopic effect and 0 trail effect. In fact, it has negative trail, and it balances by itself. So this mythology about the trail and the gyroscope is not correct. Yeah, any questions again? It's more fun if you ask a question.
Yes, I mean, so when we ride a bicycle, I guess there's a lot of feedback and so on, right? That's very different from this.
Right. So this says a bicycle can balance itself. When you ride a bicycle, your hands are on the handlebars, and you can shove the hands around. And one question is, does this self-stable property of the bicycle help you ride a bicycle? And I used to firmly think yes, and that's why we motivated this research that, oh, this is part of bicycle design, it's very important. I now think the answer is no. It's kind of an accident of history that bicycles can balance themselves. The key thing is for these biologically stabilized systems is that any instability has to happen with a characteristic time, which is longer than about 1/3 of a second or 1/2 of a second, because our control loops take about 1/3 of a second or 1/2 a second. So in terms of the evolution of the design of the bicycle, surely that evolution pushed the bicycle to design that where the instabilities were slower than 1/3 of a second, 1/2 of a second or slow. That they actually pushed it over to the other side that made it stable, I think is an accident of history, which is not important, which is a big change in my thinking. I thought it was really important. I don't think it is anymore. And one way you can tell that actually from looking at this plot is a typical bicycle. First of all, it's only self-stable down to a speed of say 4 miles an hour, and you can ride the bicycle down to 2 miles an hour or something like that. The other one is it loses its self-stability at something like 6 meters per second, something like 18 miles an hour. And when you're riding the bicycle, your perception is that the bicycle is getting more and more stable, and it's actually switched to being unstable very slightly. But the instability time is incredibly slow. So your detection of the stability is of this other mode, which is getting more and more stable. And this sort of slowly falling mode, you don't even feel it because you're controlling things much faster than that. But so anyway, this stability transition is invisible to all riders, is from stable to unstable. And I think this one is actually invisible also. So if this whole plot, if we said, oh, this is a very nice bicycle to ride, if we just took this whole plot and just moved it up so it was barely unstable all the time, I don't think you would feel the difference as a person riding a bicycle. Does that address your question? Okay. So now let me go on to a different problem, but that uses some of the same vocabulary. So here is the first cat video. It's from 1894. The first thing they did with a camera, besides taking pornographic images of naked people, was to do photographs of animals. And here they drop a cat upside down and they watch it land on its feet. So this phenomenon has been known for a long time. And this is, first thing you want to do with a movie camera is figure out things about the world that happen too fast to see. Now, people have studied this, including using math that I don't understand. It turns out the guy who wrote this article I've made friends with since then, but I still don't understand the article. But I think this is Richard Montgomery, who came up in discussions this morning. So here's this called the falling cat paradox. So you take a cat and you hold it upside down, and it's still. And so relative to its center of mass, let's just talk about angular. When I say angular momentum, from this point on, I'm talking about angular momentum about the center of mass. It's got no velocity, therefore no angular momentum. You let go of it. The only force acting on it is gravity. The air force is negligible. The center of gravity, the gravity force effectively acts at the center of mass, has no torque about the center of mass. Therefore, the angular momentum of the cat is 0. And it remains 0 for the whole fall, but the cat turns over. So usually you think angular momentum is a representation of how much something is turning. So if something's turning, it should have angular momentum, but this has angular momentum and it has no angular momentum, and yet it turns. Okay, so that's the paradox. It's really better to call it an apparent paradox. And really the word paradox means apparent paradox because we live in a logical world. And there is no such thing as a paradox. So the existence of a paradox is a paradox, or all paradoxes are apparent, whatever it is. It seems like a paradox, but obviously somehow in the end, it's not a paradox. Okay, so let me try to explain that to you, and then I'll try to show you some experiments. So if you look at the laws of mechanics, we look at the linear momentum laws and the angular momentum laws. And let's just start with linear momentum. Force equals mass times acceleration. That's the basic law of mechanics, most basic. You can turn that into force equals d by dt of linear momentum. For a fixed closed system, the mass is constant. If the force is 0, that means that this quantity L, its rate of change, dot means rate of change is 0. So that means the linear momentum is constant. If a system starts out with 0 velocity, and if the force is 0, then we're stuck with x equals a constant. So if a system has no force on it, it can't move. Okay, now as people who don't know physics well think about things, there's a linear world and a rotary world, and the same thing happens. All the equations are the same. It's just as a rotational equations instead of translational equations. And so you write the torque is equal to the moment inertia times the angular acceleration. And therefore, the torque is d by dt of this thing. We call that h, which is angular momentum, which in physics people call that L. It's just a little, let's see, in engineering we call linear momentum and angular momentum. In physics people call this angular momentum and linear momentum. They tend to call P. Anyway, L is linear momentum, H is angular momentum in this slide. If the torque is 0, then the rate of change of angular momentum is 0. Therefore, H is a constant. If we have an initial condition that the angular velocity is 0, then the initial condition for the angular momentum is 0. So we're stuck with theta as a constant. So this is the reasoning that tells you that if there's no torque and you have 0 angular momentum at the beginning, you can't turn over. Okay, so what's wrong with this reasoning is that this reasoning just assumed a single particle, and this is just a single rigid object, and the cat is not a single rigid object, it's a deforming thing. And so neither of these derivations really apply. So now you try to apply this reasoning to a more general cat. So now we have a more general picture of a cat, and we're going to think of a cat as made up of lots of particles, 100 million, 10 to the 23rd particles. And we're going to look at these the equations. So if we look at the forces on a system, it's the sum over all the particles of the mass times the acceleration, and this is all the forces, external forces. That's d by dt of this term called the linear momentum. So this is what's L dot. Well, if the force is 0 and the initial linear momentum is 0, then we can take this thing and integrate it twice, and it tells us that this term here is a constant. And what is this? This is the position of the center of mass. So if the sum of forces on a system is 0, it doesn't matter what's inside that system, what internal forces, what car engines, muscles, whatever are going on, the center of mass can't move. Okay, so that's a correct theorem. There's a step that's missing in the theorem, which is that the internal forces somehow cancel, but that's one of the basic axioms of mechanics, is that the internal forces cancel. Or another way of saying it is the basic axiom of mechanics is for all systems, no matter how many particles they have, the sum of the external forces is the rate of change of the linear momentum, which you can express in terms of the center of mass velocity. Now you try to do this in the angular momentum world, and we have the torques, which is the position of all of the particles relative to the some point C, let's say the center of mass. These are the external forces. This turns into this R cross MA term. This R cross MA we can write as d by dt of this term here. So it's d by dt of R cross MV. That's the rate of change of the angular momentum relative to point C. Okay, now if the torque is 0 and the initial angular momentum is 0, that means that this term here has to always be 0. That's this term here. That means the angular momentum has to always be 0. Now up here, when we said this term had to be 0, we could turn that, or that the linear momentum always had to be 0, we could turn that into saying the center of mass position is constant. This equation here is an equation that has positions and has derivatives in it. So it's a little bit like the constraint equation for the Chaplygin-Sleigh. It's an equation that has derivatives in it, but we cannot express it as the time derivative of an expression without derivatives in it. So linear momentum is the rate of change of mass times position of center of mass. Angular momentum is not the derivative of anything. So this idea of the linear world and the angular world just being in parallel and equivalent universes is not true once you have many particles. So this is people call this a non-holonomic constraint. You can argue about the vocabulary. The argument goes like this. Angular momentum equation is this equation. we're stuck in this world with following the angular momentum balance equation, and therefore it's a constraint. So this is a constraint equation. And back when we had the car with the wheels, we had some motion, and then the motion was constrained. So in that sense, this is a non-holonomic system, and the car is a non-holonomic system. Both of them have equations with derivatives that you can't integrate. I don't like that vocabulary. I don't like thinking of this as a constraint. I like thinking of this as conservation of angular momentum. And constraint, I save the word constraint for geometric constraints, but it doesn't matter. It's just a matter of word choice. In some sense, this is equivalent to the other one in that it's a non-integrable equation. In some sense, it's not, because the place of momentum balance in mechanics is different than the place of geometric constraint equations. Okay, so what this says is that saying that the angular momentum is zero does not tell you anything about the configuration of a cat. Now, the fact that it doesn't say anything, maybe there's some other law that says something, but that reasoning that makes it feel like it can't turn over is not right reasoning. So the simple way to say is how does a cat turn over is, even when there's no torque on it, is why not? Whatever you thought was the reason I couldn't turn it over was wrong reasoning, because the right reasoning, which is on this slide here, says that there's nothing stopping you from turning the cat over. So that doesn't really tell you how a cat turns over, but it takes away the puzzle. Right? It's not a paradox. You don't actually have to think it out. You say, okay, there's no reason it shouldn't be able to. There must be a way. But we can get into it in a little more detail. Okay, so how do you see this? Well, Tom Kane, that same guy who gave a lecture at Cornell about the braking car, and I raised my hand and said, I know, because I did the experiment and turned over my truck. That same guy was interested in the falling cat problem, and he had a graduate student, and that graduate student became an astronaut, and that astronaut went and did falling cat experiments. So first, let me show you a real falling cat experiment so you can see it. This is a video. This guy's name is Destin, and this video is called Smarter Every Day. And he drops a cat from slow motion. It's very beautiful. Okay, so he dropped a cat, and you see what it does. He lets go. The cat does something. There's no torque on it. The air resistance is negligible, but it does some weird distortion. His cat is flying, twisting around. His body is twisting around. And then it lands. If you listen to the sound on the video, Destin, who's a generally smart guy, says, notice how it sticks out its legs at the end to stop the rotation. That is wrong mechanics. That's a different problem, which is the ice skater, which slows down and has angular momentum. And if you have angular momentum and you stick out your arms or legs, your angular velocity decreases. This cat has zero angular momentum the whole time. Sticking out the legs has no effect. The reason it stops rotating is because it stopped distorting its body. The reason it sticks out his legs is it doesn't want to slap his tummy on the ground, not because it's stopping the spinning. So Destin is usually right, but he's wrong about that one. Okay, any questions about the falling cat? Just the falling cat experiment. Yes? Yes? I think the tail plays a role. And you could say it's significant in that the cat, he said it looks like, I'll repeat all the questions. So he asked, looks like the tail does this, it plays a significant role. The tail is consciously or unconsciously is being actively moved by the cat. When you say plays a significant role, it's a little confusing on these biomechanics problems, because when you're trying to do something and it's hard to do it, you use every last little bit of available motor action. So I think the tail plays a role. It's not clear there's a dominant role. The usual explanation, which I'll show in the next video, is that the cat distorting its body. Quantitatively, I don't know the relative value. Psychologically, you're deceived by the cat tail because it makes a very large motion. I can give you an example like that with human beings, is if you're at the edge of a cliff and somebody pushes you, and you're about to fall over, you swing your arms like that, and you say, it looks like the arms are playing a significant. Well, you're spinning your arms like crazy because you don't want to fall down and die. But that doesn't mean it gives you a very big effect, right? So you can measure the effect. You know, swinging your arms can move your center of mass a couple centimeters, but that might be all you need to get the center of mass back on this side of the edge of the cliff. And bending your body also gives you something, and avoiding that situation does something more. Okay, so here's a this guy, Adam Trzymczewski, made this video with my help, but he did all the work. This is trying to just explain how it goes. So you can just read the text. There are no external torques acting. I guess I'll read it out loud. Okay, the total angular momentum is 0 all the time. And if you look at that, you can see there's two competing effects. Sort of the gross motion of the body as a stick, and then the twisting along the axis. So the right is what the cat looks like it's doing in space, and the left are those two different motions, which are counter to each other. So the cat does those two countering motions, has 0 angular momentum, and then turns over, and the angular momentum adds up to 0. So from the cat's point of view, it's doing this body twisting maneuver. Okay. Any questions about this? So this is the usual explanation with no tail in it. I think this probably dominates, but I'm not positive. I didn't do a quantitative calculation. Okay, any questions about the falling cat so far?
So it's 0 angular momentum because the two halves are going the.
Say again?
It's 0 because the two halves have opposite angular momentum. Is that?
That's correct. So here's the cat, the two parts of the body. One part of the motion is this, and another part of the motion is twisting along the axis of these two parts. If you think of yourself as a cat floating in space, and you go like this, well, if I did this in space, I would have an angular momentum in this direction. But if I started in space with no angular momentum, I couldn't be that I all of a sudden have angular momentum in that direction. So the result of my trying to move my body like this is that I have to get that negative angular momentum a different way. So if I'm in space and I go like this, then a result of that is that I go like this to keep the total angular momentum 0. Okay, now what I just did was I showed you that when we look at the falling cat, it's in 3D. It looks like a very 3D phenomenon. But looking in from the cat's head, looking in this direction, it's a 2D phenomenon, right? We're looking at angular momentum about an axis, which is along the axis of the body. So I thought to myself, can we do experiments without going into Skylab, kind of expensive experiment? Well, let me show you what happens in Skylab. First, let me show you Skylab. So Skylab, you can do the experiment, but this is an expensive way to go. This video is playing, fortunately. So here's Tom Kane, student up in this Skylab. And he's in the middle there. And he's just floating in the air, just showing how he can deform himself. And then he'll start doing falling cat kinds of motions. Here's one way he can rotate his body. In this case, his body motion counters his arm motion, or his body motion. So that's not so unintuitive. But then he can break the symmetry other ways. So his leg does one thing, and it would have angular momentum, but he has to cancel that, so his body twists in another way. Then, this last part is like the most interesting part. He's learned that by deforming his body, he can locomote in a rotary way. He can reorient himself any way he wants, even though he's not touching anything. So without getting any external torque. Then he gets kind of tired of that. And I don't know whether they're joking around or whether this is him really panicking. But after he's done this experiment, he says, let me out of here. And he tries to move sideways. He can't do that. He's a prisoner in there. So it's a way you could make prisons. It's not that you have walls, it's that you have nothing. And you put somebody in the middle of a prison that's got nothing, you can't get to the side of it because you have nothing to react against unless you take off your shirt and throw it against the wall. Okay, so these, he doesn't show the cat distortion, but he has body distortions that turn around in space. So I wanted to try and do sort of terrestrial experiments of this type. And you can do these terrestrial experiments with these angular momentum platforms. So there are various classes of platforms that you can do these with. Let me show you here. So you can buy these platforms. Who has not seen a platform like this? Who has seen a platform like this? This is the other way. Who's seen a platform like this? Raise your hand. Who's never seen one like this? So these are used in supposed physics demonstrations of angular momentum. And so the purpose of these of these platforms is they're supposed to be low friction. You stand on them, you do something holding a bicycle wheel or somebody pushes you or something. And they're supposed to demonstrate conservation of angular momentum, like angular momentum goes from a bicycle wheel into your body. But in principle, they are demonstrating conservation of angular momentum. And what happens is if you look at videos on YouTube of this thing, they're really bad at conserving angular momentum. So because this has a lot of friction. So if you have one of these platforms, you can locomote by twisting your body slowly like this and then jerking it back. And then it will slide on the bottom and then I'll be in this orientation. I turn this way and I jerk back. So I can turn without anything on the outside. But you notice in that experiment, I start out by going like this. So I start out by getting angular momentum. Where does it come from? It's a reaction with the ground because there's friction down there. So immediately these platforms, they demonstrate lack of conservation of angular momentum because of friction. Well, some people realized that, and they made these much higher quality platforms. So this is a platform that has a really good bearing on it. Say again? This is resting on the ground. No, it's not. It's just resting on the ground, and these are just the feet. They're just feet. There's a little bump on the bottom, and then this platform is smaller than this radius, so you don't tip it over. And there's a really nice bearing down underneath here. Really nice bearing. Whereas this is a bunch of ball bearings, and it's a pathetic product, and nobody should have ever invented it. It's like a bad product. Okay, so. That cheap platform doesn't work well. I think I have here a video of standing on that cheap platform. Let's see if I've got it. No, this is showing how good the good platform is. So here's a good platform, and you're seeing how good the bearing is. Okay, so now I take that platform and I stand on it. And this is at Cornell. And at Cornell, it turns out that there are these vortex fields. And if you tap into the vortex fields, it's a psychological thing, but it's an interaction between your brain and the atmosphere. You can get angular momentum, and it goes into your body, and you start spinning. And it takes a lot of concentration, but if you really concentrate hard, there's usually, in any given environment, there's usually opposing vortex fields, and you can tap into the opposite vortex field. It takes a certain kind of concentration, and then you get torque on your body, and you build up angular. So it doesn't violate conservation of angular momentum because it's a vortex field combined with your body that gives you this angular momentum in these two directions. Okay, so I don't even get to the point of the falling cat demonstration because the falling cat is only an interesting demonstration when your body has constant zero angular momentum, and the vortex fields are interfering with that. So we couldn't even do the falling cat demonstration with this. Okay, so puzzle. Okay, in case you didn't know, I was joking, right? So I could extend the joke though. If I had the platform and I put it right here and just put it on the floor, and I've done this now probably 10 times, I can stand on it and I can find the vortex field and I can do that demonstration. Okay, so does anybody, if you know the answer, not allowed to say, does anybody see what the problem is? Like there is no vortex field, right? Either here or in Ithaca. So what's the deal? Say again? It's tilting. So how does the tilting affect it? Right, so this bearing is very good, and flat ground is not very flat, and this floor is not flat in my experience, and all it has to be is tipped about ½ a degree. So if you imagine, just to exaggerate the picture, imagine that this is down here, tipped way down in this direction and way high in this direction. If I stand on this edge of the platform, the weight wants to fall down here. If I stand on this edge of the platform, it wants to come back around. So if I stand leaning towards that spot, it wants to fall down this direction. If I stand leaning towards this spot, it wants to fall this direction. So when I was tapping into the vortex fields, I was leaning that way, which is when you're standing on that platform, I'm leaning that way, but then the platform turns and I have to lean that way. And then the platform turns, I have to lean that way. And the platform turns, I have to lean that way. And you can't see me do it because I'm looking so unstable anyway. And then when I want to go the other direction, I lean on this side and then it's perpetually trying to fall this way. A way to think about that is that this bearing has an axis right up the middle, and gravity is a force that acts on my center of mass, and it's off axis and slightly tipped. So here's the axis of rotation. Here's the tipped a little bit. Here's the gravity. It has a torque about that axis. So I am getting angular momentum about the axis of rotation of the platform. Platform, axis of platform, tip the platform, gravity force, I get it off axis, so it has a component that way, increases the angular momentum about the axis of the platform. Okay, and if you want to, I don't think you can see me doing it, but I'm doing this consistent leaning to one side and the other side. Okay, so for doing a falling cat demo, the platform is problematic because you have to get it just level. And again, if you look on YouTube of people with these platforms, some people with these good platforms demonstrate the lack of conservation of angular momentum. Like they do the whole experiment with the bicycle wheel. At the end, they're spinning, even though they started out not spinning, because they haven't leveled the platform first. You can sort of see that I'm concentrating on leaning, but it's hard to see which way. Okay, so I had this idea that I could make a self-aligning bearing so it would automatically level. So I thought, okay, I want to do this experiment, and I don't want to have this leveling problem. What I'll do is I'll hang a bearing from the ceiling. And if you hang something from the ceiling on a hook, it's free to swing. So that means moments about this axis and this axis are zero because I've got a pivot. And then I hang and I have a bearing, and moments about this axis are zero. So that pivot cannot transmit torques in about any axis. Then I hang from it, and even if I get off center, the gravity force is parallel to a vertical line through the hook. So I should not get from gravity any angular momentum about a vertical axis through the hook. Take the hook, look at a vertical axis, gravity is parallel to that, and the hook itself is free to swing this way, free to swing this way, and I have a bearing. So that was my great idea, and I asked my wife to do a demo so we could demonstrate the falling cat phenomenon. And this was one of the early experiments. So this is hung from the ceiling with this little bearing here. And I asked her to do this falling cat move. These are pajamas that I sewed myself for her. Okay, so then she does the thing. And I said, keep going. And this is so far, it looks like what we're supposed to see in the falling cat. It looks just like the falling cat. I said, well, keep going. And she goes, I'm getting tired. I said, well, keep doing it. She goes, I can't do it anymore. So then should be that when she stops, there's zero angular momentum, right? So she stops swinging her legs. Okay, any theories? Okay, now why would friction at the pivot do that? That was your last answer.
I don't know why it would do it, but I don't see any other.
There's no source of torque, right? Okay, so does anybody want to make a comment about this? Anybody else see? So it looks like the demo is pretty good at the beginning. So just looking at it so far, what you see is her legs, looking down on it, her legs are rotating clockwise in a circle. And looking down on it, her body is spinning counterclockwise. And those two add up to zero angular momentum, approximately. As she goes, though, her legs keep doing it, but her body slows down. And towards the end here, her body is almost not rotating at all. So she has a large clockwise looking down angular momentum. So when she stops distorting her, moving her legs around, all that angular momentum then goes into her upper body and she spins fast. But if you watch her spinning fast, it slows down. It's not like that picture I showed of me standing on that bearing. Why does it slow down? Well, it's air friction is negligible. It's because of friction up here. So what happens is, in this first part of the experiment, looking down on the experiment, looking down, her legs are going clockwise and her body is going counterclockwise. That means there's a friction force that's in the clockwise direction on this hinge. So if there's any friction, it opposes the rotation of that bar. So the bar is going counterclockwise. The friction is opposing that, so it's giving a clockwise torque. That means she's getting, as time goes on, the integral of torque with respect to t is positive. So she has more and more clockwise angular momentum. Where do you see that? It's in her legs. Why is it clockwise? Because her body has stopped spinning. So she's getting, over this whole period of time, so we take the integral of the friction torque with respect to time. Friction is approximately independent of velocity. And so she gets the integral of torque with respect to time is just accumulating, no matter how fast she's turning, just as long as she's turning a little bit. And then all that angular momentum goes into her upper body, and then eventually it goes back into friction, which stops the motion again. Any questions about that? Clear? Okay. So I've tried this with a number of people, and it works. Here's this is my daughter, who's from Pune, adopted from Pune, and here she is in a more controlled environment. And then she does the falling cat thing, and she's very good at it. But eventually her upper body slows down, and then and it sort of looks like there's a spring effect up here, but it's not a spring effect. It's just a friction effect. Okay, so I was at a conference one time. If you want to disprove the spring effect, you think it's a spring sort of storing up the energy. Here's an experiment to show it's not a spring effect. Prachi again. She does this thing. She's building up angular momentum in a clockwise direction, looking down. Freeze her, see if it's stored up in a spring, and it's not stored up in a spring. Okay, so I was at a meeting with the Gage Theory of a falling cat guy, and it was in a beautiful place. Everybody went hiking and skiing, and I went to a hardware store and bought the equipment to do a demo of this. So I went to the basketball court, and I hung a bearing that I bought at a climbing store, and I made this trapeze and everything. And you can see I got a very good bearing this time. So it's not like that bearing I had in my living room. This bearing, you just have a little angular velocity, and it turns and doesn't slow down. It's a really good bearing. So I got this basketball player, see if we can see him again. Got this basketball player to do, you can see again how good the bearing is. It just turns and turns, right? So I got this basketball player, and I said, okay, will you do this demo? And I thought maybe this would be either a good demo, like I finally achieved my goal of showing this falling cat in a terrestrial experiment using this idea of a bearing that aligns itself. So I get all three moments of self-leveling. It conserves angular momentum. It should all work out. So I got this guy, this basketball player, and I said, just do this cat move. And he sort of got the hang of it. And he's turning clockwise, looking down. And if there was friction, it would be in the counterclockwise direction. And he says, I'm really building up my angular momentum. I said, you are not. He said, yeah, I am. I said, yeah. He said, I am. I said, you're a basketball player. I'm a professor. And then he stopped minning, and he was building up his angular momentum. Okay, so this is different from the experiment I showed before. In this case, So when I did the one in my living room, there was the leg motion going one way, the body motion going the other way. There was a torque building up opposite the superficial motion of the body. Right, so if there's friction up here, it should be in the counterclockwise direction. So the angular momentum should be building up in the counterclockwise direction. Yet when he stops distorting, he has angular momentum in the clockwise direction. Okay, do I need to explain that again, how that's different from my living room experiment? In the living room, the legs go one way. It's hard to see for him which way his legs are going, but the legs go one way. The upper body goes the opposite way. Friction opposes what the upper body is doing. So angular momentum is being built up opposite the direction of the body. So when you stop distorting, the motion is opposite the direction of the body. That's what happened in the living room. Here, he stops. He tells me he's building up angular momentum. I tell him nonsense because he doesn't know mechanics and I do. And then he stops distorting. And he has angular momentum in the direction his body was moving. And I can show that phenomenon with the more controlled experiment. Yes? Say again? Where is what? In my case in the living room or in this case?
In either of the case.
Okay, in either of the cases, and same with the whole falling cat phenomenon, there's sort of two contributors to angular momentum. One is viewing your body as two sticks. And let's say if you just take it, I'm doing it with my upper body, but hanging there, it's the lower body. If I just bend around like this, and you look from the top, you see particles going in circles like this about the center. So the angular momentum's in my body. With my wife in the living room, it was her legs going around like this. So you track her legs, there's angular momentum there. The other place it can be is you just look at the upper body and it's turning like this. And if the falling cat is according to the cartoon or according to the space station or according to the cat falling, these two angular momenta cancel. So you have zero angular momentum at the beginning, in the middle, and the end. And in the case where I had friction, her legs were going one way, her upper body was going the other way. The upper body was what was determining the motion of the bearing. So the friction was opposing just one of those terms, the upper body term. What happened is she was doing her legs, her body was moving slower and slower. So eventually all of her angular momentum was in her legs. Then when she froze her legs, then it was shared between her legs and her body and she went spinning like this. Now with this basketball player, he's doing his thing with his legs. His body is turning one way. It should be that he's building up angular momentum the opposite way if it was like my wife, but instead he stops distorting and he actually was building up angular momentum. So the only source we had for angular momentum is air friction, which is negligible. I really think it's negligible. Somehow he's getting angular momentum in the direction his body is moving, which is opposite the friction in the bearing. I don't know if that addresses your question directly or not.
Yeah.
Is this good enough?
Yeah.
Okay, so anybody have any theories about this? So I can give you, I can give you, I'll just show you more videos of the phenomenon. So for it to be interesting, you have to see a puzzle. So I guess the first thing is, does anybody not see what the puzzle is? So the puzzle, let me just say it again. The puzzle is my subjects start with zero angular momentum. They do an experiment. They end up with angular momentum. The only source we know is friction at the bearing, which should mean that the motion of their body when they freeze their legs should oppose the motion you saw before they froze the body, which is what I saw in the living room. But now this is a much more controlled environment. So here's now my wife again, and she does this thing. And she's hanging from that really good bearing. And then she stops distorting. And she keeps going in the same direction. It's the opposite of the living room experiment. Now I do the same experiment twice, I get opposite results. There was a change in between. right? I bought a different bearing, but you can buy very low friction bearings. You can't buy negative friction bearings, right? Those are called rocket ships or perpetual motion machines. It was a low friction bearing. It wasn't a negative friction bearing. Does anybody see where this angular momentum is coming from? So could anybody need help with what the puzzle is? You're supposed to see a so-called paradox, right? It's an apparent paradox, but we don't. Does anybody raise your hand if you see what the problem is? Okay, raise your hand if you're not clear on the problem. You're not quite clear on the problem?
So the earlier she was going in one direction, now she's going the other
Going in
way.
one direction, her body's going one direction. When she stops distorting, she keeps going in the same direction. So the basketball player did it, and I said, yeah, yeah. And then I tried it. Not very gracefully. And I had just a little bit of motion in that direction, not like I wasn't as good at it.
Andy, there's a question, I think someone.
What?
There's a question online.
I don't know how to address.
Maybe Mukund, you can just ask your question.
Yeah, is it coming from the suspension points of the rope?
Yes. Talk about the suspension point of the rope, please.
So there seems to be an oscillation at the same frequency as the angular oscillation, which may be somehow not sort of canceling itself out.
But where is the angular momentum coming from?
So somehow over the course of an entire rotation, these things are pulling. So she's always in one direction facing one way and the other direction facing the other way to the center point.
It's something like that. I think I'll give you some credit and then I'll try to explain it. Okay, so when I did the experiment in my living room, by the way, who asked that question? Just so do I know you?
This is Mukund Tatai. No, we have not met. You know my brother Venki.
Oh, Venki. Where do I know him?
From Cornell.
Oh, so, yeah. Okay.
He was a student. So was I.
Okay. Talk to me sometime. Okay. So when I did the experiment in the living room, this point was fixed. When I went to the basketball court, I hung it from the ceiling, but the ceiling, I couldn't screw into the ceiling. So I hung it with two ropes. And let's see, I'll show you in this other thing. I hung it with, you can just barely see here. Let me see if I get this, a good picture with the two ropes. You can just barely see, there's two ropes coming down here from the balcony. So I hung it the same way that I'm showing you in this video here, that from a point that was free to move back and forth. So when we have this conservation of angular momentum, it holds relative to the center of mass, no matter how the center of mass is moving, and it holds relative to a fixed point, or a point that's moving at constant velocity. This point is not a fixed point. So even though if we take a vertical axis through this point, straight down, the gravity force has no moment about that axis. The bearing is good. It has no moment about that axis. It's free to swing back and forth. So there's no moment about that axis from gravity or from the bearing. But this point is not fixed in space. There's no theorem of conservation of angular momentum about an accelerating point. So if instead you pick a point in space here, and the point you pick, let me just pick this. The point you pick, I have to freeze it, a random thing, is a fixed point that's in space there. An imagined point at the tip of my arrow here. And we do conservation of angular momentum about that point. If she can generate a force in that direction when it swings that way, and in the opposite direction when it swings that way, then she can get a torque acting over time. So if she just consistently swings her body so that she gets a force in that direction over here and that direction over here, she can get a torque and she can build up angular momentum. And it's not so much that the swinging is synchronous with the rotation, it's that the forces she applies are synchronous with this thing going back and forth. I don't know whether it's a mechanical phenomenon or a psychological phenomenon, But everybody who does this is trying to turn. And at some subconscious level, they learn to do this thing of applying a torque this way on this side and this way on this side and build up angular momentum. So you're building up angular momentum about a center point where my cursor is by this synchrony of the sideways force and the swinging. It's not the synchrony with the rotations. And every single person, it's a sample of 5 so far, but every single person has that effect. Okay, so now we want to say, now we know everything. It should be that if we take a good bearing, and put it on the ceiling, everything should work, and we can do a successful experiment. And this is the most boring part of the talk, is that, yes, you can. So now it's on the ceiling. Now I have the good bearing with low friction. She does the cat thing. She's not getting tired. Her legs are going one way. Her body's going the other way. It's perfect. Her angular momentum is 0. And then she stops deforming and she stops. Right? This is the way it was supposed to work. Screwed up on the high friction standing platform, too much friction. Screwed up on the tip platform, we get a gravitational torque. Screwed up on the hanging from the ceiling with the bad bearing. Screwed up on the hanging from the ceiling with the good bearing, but a moving support. Finally, we take the good bearing on the ceiling without a moving support, and the whole thing works. And it turns out, if we go back to the platform, but we level the platform, so you have to do the experiments to get that ½ degree out of there by putting little shims under there. You can do it on the platform if you have a good platform. If you want to do this experiment, it's cheaper to do it with the hanging bearing than with the platform, because these cost a few $100. The hanging bearings only cost like $50. But so I do the cat thing. I turn. I have no angular momentum. I stop distorting. I have no angular momentum. And this is it's a very good bearing, right? If I just turned a little bit, I would turn freely on this thing. Okay, so that's the basic talk. There's a couple cute little things that you can observe about this. One is what if the friction wasn't Coulomb friction, but it was a linear viscous friction? So take the case where the hinge is on the ceiling, but the friction is proportional to the velocity of rotation at the ceiling. Okay, so if that's true, we have a friction torque proportional to velocity. So the integral of torque with respect to time is the integral of the velocity of the hinge with respect to time. If you start stationary and you end stationary, then the integral of the torque is 0, which means the integral of the velocity is 0, which means that however much you rotate winding up, you'll rotate exactly that much winding down. Okay, so you look at the torque of the system, it's the rate of change of angular momentum. The torque is C times the rotation rate of the hinge. That's the rate of change of angular momentum. The total change in angular momentum is the total change in angle. But if you're stationary at the beginning of the experiment and stationary at the end, the integral of torque with respect to time is 0, so the change of angle is 0. So this says if you had linear viscous resistance, you would always end up winding up some, winding back the other direction, and coming to a stop right where you started. And then the next paradox is, that's true no matter what the dashpot constant is, no matter how small. So the limit as C goes to 0 gives a different answer than C equals 0. C equals 0, you stop deforming and you just stop. C not equal to 0, you spin back, the friction spins back. So this is the last paradox. So this says there's friction, you're building up angular momentum, you stop distorting your body, you spend that angular momentum, but in building up the angular momentum and spending it, the net change in angular momentum is 0. Therefore, the net frictional impulse is 0. Therefore, the torque with respect to time is 0, but the torque was proportional to angular velocity. So the integral of angular velocity is 0, which means the net change in position is 0. For any C greater than 0. But if C is dead 0, you rotate and you stop. So if you do an experiment, you do smaller and smaller C, you get one result. You get C0, you get another result. How is that paradox resolved? Okay, maybe I'll just leave that one for you. There's another one that's similar to that for boats in the linear case. Okay, so what do you get? With no friction, rotary locomotion is possible. You can turn without friction. Linear locomotion is impossible. I can't make myself go here to there without forces from friction from the environment. I can turn around. With linear viscous friction, rotary locomotion is impossible, as I just explained. You come back to exactly where you started. And linear locomotion is also impossible. It's the famous boat problem. How far does a boat move if you walk one end to the other? Okay, so you can go through all these different conclusions. And here is a summary of the talk. Non-Holonomic constraint is a not-whole constraint, non-integrable. Even Ramanujan couldn't integrate it. It just doesn't integrate. You can get to places you can't move. Another way to say what non-holonomic means is it's a restriction on velocities that cannot be expressed as a restriction on configurations. And the main examples and the only examples are skates and rolling. And then the falling cat is zero angular momentum doesn't imply zero rotation. And that's the talk. So I'd say, what did I do? I only went 20 minutes overtime. I would say I should stop the talk right this minute, take a 2-minute break. Don't come up and talk to me. If you want to talk to me, just stay here and then I'll keep talking to anybody who wants. So I want to take a 2-minute break right now. Anybody who wants to leave, and then I'll keep going after that. Is that okay for a system? Okay, so sorry I went 20 minutes late. You have 2 minutes to leave.
Yeah, so that was a really fantastic talk. So let's thank Andy for this amazing talk. So maybe we can still take some questions now.
We'll let people leave gracefully.
And then people
You won't look at them and I won't.
So people who are online can also ask questions, and those who are here. Yeah, any questions?
We take a break.
I think there's a question online. So there's a
wait,
question online. What finally balances the bicycle from?
Okay. So what finally balances the bicycle? So there are three. I have a whole lecture I can give about the bicycle, and if you go to my web page, there's hundreds of pages of stuff you can read in my friend's web page in Holland. Well, if you say what balances the bicycle, there's three different bicycle balance problems. One is how does a bicycle balance itself when there's no rider on it? Another is how do you balance a bicycle when you are riding with no hands? And a third is how do you ride a bicycle when you're riding with hands on the bicycle? And so at one way of looking at it, the way a bicycle balances in all three cases is because of steering. So it balances because it turns into a fall. So if you look at all the different effects, the radius of the tire, the trail effect, the angular momentum effect, they're all completely dominated by steering. So what balances a bicycle steering? So the question of what balance the bicycle reduces to, what makes the steering be correct? So when you are riding a bicycle, you have a control law. Roughly the control law is turn into a fall. When you're riding with no hands, you don't have control over the steering with your hands. But if you bend your body because of the trail, that gives you some authority over the steering. So you're bending your body, causes the steering, causes a contact point to move sideways, and that makes it so that the wheels move back onto the center of mass. And then if you say, what finally balances a bicycle that has no rider on it, the self-stability, like the videos I showed, well, the equations are incredibly complicated, and the stability is determined by the roots of a fourth-order polynomial, and there's a big mess there, and there's no simple message. What we showed is that if you take away the gyroscopic effect and the trail effect, you can still balance. But is there some simple mechanism? And the answer is there is not a single mechanism. The trail has some contribution. The angular momentum of the wheel has some contribution. The fact that the center of mass of the front assembly might be forward of the steering axis and low, and the center of mass of the back of the bike might be high. So when the bicycle starts to fall, the front assembly tries to fall faster, which steers the bike. That's another effect which contributes. Another one is about this coupling of moments of inertia that you're rotating about axes, which are not principal axis of inertia of the rigid object, and that causes a coupling between the lean and steering. So there's 4 or 5 effects that contribute to the relationship between leaning and steering. And what we showed is that 2 of those effects are not necessary and they're not sufficient. But what really does cause the bicycle to balance is that you have to have the right combination of all those effects so that when the bike falls to the right, it steers to the right amount to balance. Does that answer the question, the person who asked it? So we know what balances a bicycle. The roots of the 4th order characteristic equation are the 4th order linear differential equations. And we know all the terms that go in, and we know that the mathematical model is pretty close to the physical model of the bicycle. We don't know some simplifying words to describe what combination of parameters does that. Who asked the question and did the job for you?
Yeah, so he's happy with the answer, I think.
Has he answered it to everyone? Yes, good. Okay, next question. Yes. So I'm willing to stay here forever. So you guys should just, as you get bored, you should just leave.
Yeah. On children's bikes, generally they put training wheels on the back.
Yeah.
Is there any argument like for maybe trying to put it on the front instead?
I've never heard that question before. I don't know any argument for putting on the back, but there's good reason not to put them on the front. There's good reason not to put them on the back. I have a video about training wheels that's 3 minutes long, and I'm very proud of this video. And I could just show you this 3-minute video about the nature of training wheels. Is that all in favor of my showing you a 3-minute video? Okay, so you just have to give me a minute to find it. I think the easiest way for me to find it is to go to the World Wide Web. Okay, now I'm going to have to get the sound somehow. So this is 3 minutes long, and it's kind of dense. So it's not that I talk fast, but it's we put a lot of effort into making this information rich. Now, where's the sound? Okay, ready? Wait a second. Did you turn on the sound of my computer? Turn off the sound of my computer. We don't want the sound from my computer. Don't share a computer sound. Okay. I'll try it. I'm doing it this way. Or maybe you do want to share it. That's not my video. Oh, I lost this thing. Okay.
A bicycle can be adjusted to be a bicycle, a tricycle, or anything in between. The spring mechanism in the rear provides a restoring force proportional to lean. Using a so-called zero rest length spring, the effective spring constant can be adjusted by moving the attachment point of one end of the spring. Clamping the spring, infinite stiffness, makes a tricycle. Detaching the spring, zero stiffness, makes a bicycle. A person can balance and steer a normal bicycle, navigating the course and staying upright, counter-steering to start a turn and leaning into turns. When we detach the spring of the bicycle, it is in bike mode and can be balanced and steered like a bicycle, counter-steering and leaning into turns. If we clamp the spring, effectively making the bicycle into a tricycle, it is held upright and can also be steered, with the centripetal acceleration balanced by the outer training wheel. At some intermediate value of stiffness, the spring restoring torque cancels the gravity capsizing torque and the bicycle is, for balance purposes, effectively in zero gravity. When not going forwards, it is a neutral equilibrium for leaning. But this vehicle, a bicycle in zero gravity, cannot be both balanced and steered. Attempts at steering the bicycle tip it. It can't be righted and also steered in a desired direction, and steady turns are impossible as there is no torque available to balance the centripetal acceleration. As best we can tell, nobody can steer the bicycle around the simple obstacle course. The first attempt at a steering causes a lean which can't be corrected, at least not while trying to steer in a desired direction. A controlled bicycle is really just an inverted pendulum. It is balanced with sideways accelerations of the support by steering on a bicycle, which, if coordinated, can also control the position of the base while balance is maintained. However, if there is no gravity, as for a horizontal pendulum, the sideways displacement and the pendulum angle cannot be controlled independently. They change in proportion to each other. In fact, there's a point on the pendulum stick which can't be moved at all. The bicycle is really the same thing as a gravity-free pendulum. Assuming friction and so on are negligible, if we start from an upright position, the lean and sideways displacement of the ground contact point are always in proportion to each other and opposite. So changing direction would cause both an ever-growing distance from the original line of travel and an ever-growing lean angle. Riders don't tolerate this. Instead, they maintain balance and are stuck going about straight. So gravity, superficially the thing that makes it hard to ride a bicycle, is the thing that allows you to steer it.
So what does this have to do with training wheels? Now I can turn off the computer sound. Okay, what does this have to do with training wheels? Oh, it's still coming out. You have to, you want, what? It's, sound is coming in. I'll just ignore it. So training wheels are kind of backwards from what you're riding a bicycle. So it's not like training wheels, like if you phase them out gradually, you get to a point where nothing happens. So control-wise, training wheels are teaching you all the wrong things. So forget putting training wheels in the front. Training wheels are a bad idea altogether. Training wheels, you go around a turn and you have to fight being pulled out of the turn. Real bicycle, you lean the bicycle into the turn. It's a totally different coordination. So training wheels, the only thing they're good for is to act like a tricycle just so you get used to pedaling and standing there. They're not, they help you negatively learning how to ride a bicycle. As far as putting the training wheels on front, I don't, seems sort of like the same thing, but I don't know. So who asked the question about putting the training wheels in front? Yeah. I think training wheels are a bad idea. I think putting them on the front is probably just as bad an idea. Does that address your question? Yeah.
And I had a question about the non-holonomic constraints.
Yeah.
So if you have a higher dimensional falling cat problem, for example.
Higher dimensional what?
Falling cat problem in 4 dimensions, let's say.
Well, I don't know what mechanics is in 4 dimensions.
Or just assume Newtonian mechanics.
Say again?
Newtonian mechanics, the same Newtonian mechanics, but 4 spatial dimensions.
I don't know what that means. So you can try the question, but the thing is, like, my understanding is so based on 3 dimensions where, like,
So maybe I'll rephrase it.
rotation can be represented as a vector, and we have rotation matrices, and so the nature of rotation in 4 dimensions is a different thing. So I don't know how to think about it.
Okay, maybe more abstractly as a mathematics. So if a constraint is non-holonomic in D dimensions,
Yeah.
can it become a holonomic, or can you remove that constraint in a higher dimension?
Okay, so how about let's not do the angular momentum. Let's not do the falling cat non-holonomic, but let's do the kinematic constraint. And then we can have higher dimensions, not higher spatial dimensions, but we can have more degrees of freedom. So the question is, if I took a mechanism that had a non-holonomic constraint, and then I added degrees of freedom to it, could it become a holonomic constraint? And I think the answer is no. I haven't thought about it before this instant, but the thing is if you take the example of a skate on a car, and then we can make higher and higher dimensions by making a train of cars, or like a 7-link pendulum where one of the pivots has a skate on it. That constraint, just by itself, independent of all the other stuff that's happening, is non-integrable. Right? There is this direction of motion that it can't go, and there are places it can get to. So the extra dimensions and other parts of the problem don't change that effect. So I think the answer, at least if in that interpretation of the question, is going to higher dimensions doesn't change things, but maybe there's some other way of thinking about it, or it does. Okay, microphone, please.
Maybe there's a naive viewpoint. So the angular momentum is like a vector. It's a pseudo vector in 3 dimensions.
Yeah.
And specific to 3 dimensions.
Yes.
Anything more than that, it's.
I don't know what I don't know how to think about it. Right?
Yeah. And so my worry was, is it really specific to 3D?
Yeah. Say again.
So this question of non-holonomic things becoming holonomic, and this falling cat problem, is this specific to 3D?
Well, remember, I have these. To me, the falling cat is not non-holonomic. It's just not. There's an equation that you can't integrate, but it's not considered non-holonomic mechanics, for example. So that angular momentum constraint. I don't know. I just don't know how to think about it in higher dimensions. I just don't know what it is, or I don't know how to think about it. I'm an old-fashioned guy living in this three-dimensional world. And then the kinematic kind of non-holonomic, I think, if we say more dimensions, like more degrees of freedom in state space, I don't think adding them can turn non-holonomic into holonomic. Yes? Do you have a question?
What should be the balancing criteria for a unicycle? You have talked about the bicycle and tricycles.
You mean how do unicycles balance? It's a question?
Yes.
Okay, so unicycles are not self-stable. So unicycles are only balanced by active control from a person. Okay, that's the first thing. You could imagine a kind of unicycle that had some self-stability if the wheel was gigantic and the center of mass is low and stuff like that. But basically unicycles are not, you don't see a unicycle riding along without a rider. So then what's the nature of the control? So a bicycle only falls over one way, which is sideways. And a unicycle falls over frontways and backwards and sideways. So you have to balance both of those, which means that if your center of gravity is out of position, front and back, you need to move the contact point forwards to get it back underneath. If the center of mass is off to the right, you have to move the thing to the right. If the unicycle is moving along forwards, so I'm moving along forwards, and I fall forwards, if I pedal faster, that brings the center of mass back underneath me. If I'm falling backwards, I put slight braking on, it puts it underneath me. If I'm falling to the left, I steer to the left. How do you steer a unicycle to the left? Is you do counter rotation with your hands, right? So you can steer like this, and then you can get back that little bit of angular momentum that let you turn your body because of the torsional friction of the tire. So the simple answer is you steer to get sideways balance, and you accelerate and decelerate to get forwards and backwards balance. That doesn't cover the case of hovering in a unicycle where you're stationary and you balance, which is very hard to balance. So it's a very high level skill. That one, the front and back, you do the same way by, if your center of mass is off to the front, you pop the unicycle forwards by pedaling forwards, same with backwards. How do you go sideways when you have that non-holonomic constraint? Is you have to very quickly do that parallel parking move. So it becomes not a continuous like control, but a discrete control. You're falling to the left, you have to do a move forward, steer to the left, steer to the right, move backwards, and move the back over here. So that's why you see the people riding unicycles when they're stationary, they're moving back and forth so they can add that correction. So the next back, they move their center mass over here, and then the next one, they move it over here. And so still, the basic control is you move the contact point under the center of mass. Front and back, you do by pedaling forwards and backwards. Sideways, you do by steering when you're moving along already. Sideways, you do by parallel parking if you're just doing it from a stationary position. Does that answer your question?
Yes, thanks.
The question was, how does unicycle balance, in case people didn't hear it?
Hi, so I have two questions. So in one of your initial videos, you showed how a moving bicycle is a stable system, right?
Many bicycles, if you tune them up and take off all the extraneous cables will balance themselves.
So, so my question is, so what role does the friction at the pivot of the steering play? So if, does it make it unstable or what?
I think there's a book by Niemark and Fufayev, which is called Non-Holonomic Dynamics. And they studied a bicycle and I think they put viscous friction in the hinge. And I think if you have small viscous friction in the hinge, it does not destroy the self-stability. In general, if you have like Coulomb friction, which is a fixed friction torque you have to overcome, that completely destroys the stability. Because if you use the linear equations of motion, that's the small motion equations, Coulomb friction is the same as locking the joint. So the balance is completely dependent on that joint being locked. And Coulomb friction for small deviations is a locked joint. So Coulomb friction is very bad for stability. Linear viscous, I think, eventually destroys it, but a small amount it can tolerate. But that's one of the demo experiments I have in the bicycles is you lock the steering, that bicycle, it falls over. It just falls over as if it's not moving.
Okay.
Equations of motion for falling of a bicycle with no steering. The equations of motion are the same if it's going forwards or if it's not going forwards. The gyroscopic effect is completely killed by locking the steering. Mathematically, it's dead. Mathematically, zero.
So in the ideal case, zero friction will make it completely stable, sort of. Is that true?
No, I mean, all our models use zero friction at the steering bearing. That's just our model is zero friction.
Mm-hmm.
So I think that, a good bicycle has very low friction there. And my experience with bicycles is that that's true. So sometimes you have bicycles that they've been in an accident and some bearing has made a little dent. The balls has made a little dent in the race of the bearings and there's a little detent. So as you're steering it, you'll feel it's like locks up and that makes it hard to ride a bicycle. It may be almost impossible to ride it, no hands. So in general, I would say, for a bicycle, that freedom of steering is, all the things that make a bicycle stable are couplings to that steering. So having freedom there is important.
I see. I have another question. So you showed that in a tricycle, so the spring constant plays a role, right? Whether the steering becomes controlled or uncontrolled completely.
I don't understand the question.
Okay, so at some critical point of the spring constant.
Oh yeah, the spring constant, yeah.
The rider could not change the direction of steering, right?
You can't steer and balance at the same time. So what happens is that when you have no gravity, the lean response to steering is exactly proportional to the directional response to steering. So you can't separate them. So if you correct the leaning, something happens to the steering that you have no control over.
Mm.
So your ability when you ride a real bicycle to steer and balance is because if you put a small steering motion in, it has one effect on the balance and a different effect on the steering, different time-dependent effect. So you can make a time-dependent motion that brings out one or the other of them. So you control the steering and balance at the same time.
Mm-hmm.
It's a very subtle thing, right? You're doing, which is just if you want to bring out a point here, you ride the bicycle, you're taking advantage of the fact that the step response of a steering input on lean is different than the step response of the steering input on direction. And by teasing those apart, you can cause a change in direction without messing up the lean, or you can make a change in lean without messing up the direction. Very sophisticated idea. Everybody's riding bicycles. We're way smarter below the ears than above the ears. So the same goes for that, my angular momentum experiment where the people built up angular momentum. I did that experiment. It took me hours and hours and hours to figure out how did people actually build up angular momentum. And they do it by this trick of not, because angular momentum is not conserved about the hinge point. If the hinge point is accelerating, but if you pick a fixed point between the two average points, then you synchronize the sideways force to be in synchrony with the swinging direction. Obviously, these people are not thinking that whole thing through, right? And everybody who's got on that has figured out how to build up the speed like in 20 seconds. So like when it comes to like motor control, I think we've got way more sophisticated brains below our consciousness than above our consciousness, right? I'm really good at this stuff and I can't think it through, whereas everybody can do it. anyway, that's a little more than you asked, but I don't know, you asked something about the spring and the, was that in the direction of your question or?
Yeah, sort of. So
The
I
dot
have
product was bigger
a
than
bit of
zero.
follow-up. So by changing the value of spring constant, is it possible that we lean in one direction and the cycle goes in other direction?
Well, I mean, there's just one spring constant where things go funny. And that's where you effectively cancel gravity. So that's where you have no dynamics of falling. So it's that the dynamics of falling is different than the response to the steering. So there's one spring constant where that happens. At that one spring constant, if I steer to the left, the bike goes to the left and I fall to the right. And that's all that happens. If I want to get straight up again, I have to steer back to the right and go straight.
Okay.
If I want to steer to the left and fall down, I can do that. If I want to lean to the right and go to the left, I can do that. But if I want to lean to the right and go straight or turn and not fall over, I can't do that. Right? Because the two are in proportion to each other. They're not decoupled. They don't have, the falling and the steering have the same dynamics. And that's what messes it up.
Thank you.
There are some questions online. There's a question.
Can you make a mechanical device? Yeah. The answer is yes. I actually bought a little contraption with springs and sticks and stuff like that. And you cock it, you hold it, and it has loaded in the springs, kind of a cat motion, and it does this little flip around and you drop it and it lands on its feet. So the simple answer is yes, you can make a mechanical device that does that. It's not some weird mechanics or, it's you need a hinge that does this. Right.
But is there a toy like that which you can buy?
I bought a toy like that.
Oh, there is a toy like that. Okay.
But it's like, some physics hobbyists, they probably sold 100 of them and one of them was to me. Like I don't know if you look for it. My guess is you won't find it on the internet now. And my guess is you won't find it in my office either. I don't know where it is, but there's this contraption that you sort of wind it up and it does this distortion and you let go of it and it falls and twists around and lands on its feet. It's not very impressive. Yes. Yeah, that was Richard Montgomery. Since I don't understand what gauge theory is, so I saw that and I put that up there as kind of a joke, and then I met the guy who wrote the paper, and I've actually talked to him for several hours, and he's trying to explain to me gauge theory. But are there any physicists here who can say in 1 minute what gauge theory is?
I sort of know what, let's say in context of electromagnetism or other theories where the gauge theory, in this context, how does it come in, or let's say?
Okay, so there's this guy, Richard Montgomery. He wrote the gauge theory of the falling cat. Okay, fine, that's done. About a year or two ago, I went to a conference and it was called Mathematical Physics or something like that. And I gave a talk on something without doing any library research. I just had a question. I thought, okay, here's my question, here's my answer. And I announced in the talk, okay, I'm giving this talk. I don't really know anything about this subject. There's probably here who actually understand this question, and you can tell me afterwards. And so I gave my talk, and my talk was about how do you define rotation for a non-rigid object? So you have an object which is not rigid. What do you mean by the rotate? You can talk about the translation very well by how the center of mass moves. Is there some characteristic of the object in its parts that you can use to define rotation for a non-rigid object? Okay, that was my question. And then I cooked up an answer, which I thought was pretty good. And then after the talk, this guy comes up and talks to me on Zoom, but still he comes up, and he says, "Yeah, you said there are people in the audience who might know this subject inside and out, and I'm that person." Okay, so that was Richard Montgomery, the same guy who wrote the gauge theory of the falling cat. And so he told me that thing which I was kind of inventing was somehow gauge theory. So I can tell you the thing that I was thinking, which he said was gauge theory, but I don't know if gauge theory is independent of that. So the idea is that there is no precise definition of rotation of a non-rigid object. But if you want to invent one, here's the one that I invented, is you take the object in some initial configuration, then later on, it's got a new shape and a new orientation, whatever orientation means. You take it from that distortion back to its original shape. And you do that fast, conserving angular momentum. So associated with any configuration, there is some shape that comes from a process of going from that distortion to the original shape, which gets you to some rotation. But that means you have to invent the process. Different processes will give you a different answer. So I think what he said is, I'm going to define the rotation of a non-rigid object as taking the initial state, going to any other state, defining the rules by which it goes back to the same shape, and then looking at the rotation between those two. I think those rules are called a gauge, but I'm not, that's what I think he was telling me, something like that. Does that sound right? Does that sound right? Something close to that? Okay, so, but I don't know what I'm talking about, right? So that's, does that make any sense to you? So somehow you try, in that case, it's trying to define rotation of a non-rigid object. So why is that relevant to the cat? Is in the process of turning, at some points in that process, it does not have the same shape it had initially. So what quantity is progressing as it's moving along? So it's a way of quantifying the progression of that rotation is having some, so that's why it would connect to what I just said, right? That sound, again, I don't know what I'm talking about, but that's my answer to your question. Okay. Now, if you're going to come up and ask me a question afterwards, you just ask it now, because then other people don't get the benefit of it. Yeah. Yes.
Hello.
Yes.
So while riding a cycle, we generally try to leave our hands and let the cycle go.
You
And
ride no hands. It doesn't mean you're letting the cycle go, but go on.
yeah, of course. I mean, my body is helping stabilize.
Yes.
But then when we are also carrying some groceries, let's say,
Yeah.
and we don't have a basket, so we put it in one of the
Handlebars.
arms.
You put the groceries on the handlebar arms.
Yeah, one of the arms.
Just a minute, stop right there.
It doesn't.
No, I ask your question, but I just want to stop the story.
Oh.
About 5 days ago, I bought a bag of fresh mangoes and I put it on my handlebars and I'm riding along and it goes, and all the mangoes went between the spokes and the front fork and they were jammed under the fork tightly in the bag. With the bag tightly on the handlebars. I couldn't roll the bicycle. I couldn't get the bag out from the spokes. And all I had was a bag of squished mangoes. So I had to take the wheel off the bicycle to get the bag out, and then I had to eat all the mangoes right then. It was terrible. Okay, that was just a few days ago. Anyways, you put your handlebars, your bag on the handlebars.
Yeah. So let's say the bag is very far away from the spoke, so that it doesn't experience such.
Yeah.
But then let's say I leave my hands and still I'm able to stabilize the bicycle somehow.
Yeah.
What I've noticed is if the handlebar is, let's say I've used the right handlebar and kept the groceries on the right handlebar.
Yeah.
Somehow my body, everything, the way, whatever I do, psychologically, whatever happens, the cycle actually, even though the cycle is tilting in the right direction, the handle is tilting in the left direction.
Yeah.
Do you know, probably, I mean, this has happened many times and never found the answer. So
I don't know if I can give you a direct answer. I mean, there are lots of counterintuitive things about right and left on bicycles. So the fact that you're leaning right, would that make it steer right or left? I don't know. You have to think it through. There's not some simple thing, oh, right is right and left is left, right? Because you're leaning to the right. There's a gravitational torque on the front assembly, and then there's the ground contact torque, and how those conspire to make it so you turn right or left. I'd have to think it through, and I don't think it comes out with a simple answer. It might be different, depending on the exact geometry.
Generally, I mean, normally if the cycle tilts to the right, the handle also goes towards this only, right? The handle will go like this.
Well, that's normally, and that's what, if the bicycle tips, let's say you sit on the bicycle and you lean like this, which leans the bicycle to the right. Normally that steers the bicycle to the right because the contact point is behind the hinge and it has then a component turning the wheel. But then you add a gravity term in some funny place. I have to think in detail which way it makes it go.
Okay.
So I guess basically, yes, I can say I don't know, but it's not, I know there might be some simple explanation. One more question back there. Now, my hosts are prisoners here, but you don't have to stay, right?
Yeah, question is simple. So if you talked about the stability of cycle, if you just let it move, if the ground is slightly tilted towards the right or left,
yeah,
does the stability change or like?
Well, I mean, all these things are at, when you talk, there's a difference between equilibrium and stability, right? So you put in some bias force, it changes the equilibrium.
So I'm saying
if you get on a slope, which is sort of equivalent to putting in a crooked gravity, the equilibrium configuration has changed. And is there an equilibrium configuration? There might not even be one, right? It might be that, or in order to get an equilibrium, you might have to add some other bias, right? So if you break the symmetry, there's no reason to expect a symmetric straight ahead motion, right? So if you break the symmetry by being on a slope, you have to do something else to break the symmetry to make it so you go straight. And then what does it do to the stability? The rule of thumb is small perturbations like that do nothing to the stability. They just bias the motion in some way that you have to compensate with some other bias.
Okay.
Right? Sort of, what if I said, oh, I put a sideways force on you, which is almost the same thing as being on a tilted ground, right? Because tilted ground is the same as tilted gravity, is close to adding a sideways force. That will change. You're no longer in equilibrium, right? Here,
yeah,
you have to lean into that, but if you lean into that, that puts a steering torque, and then you're not going straight. So you don't have the steady state solution to which you can apply the concept of linearization and stability. You don't have that fixed point anymore.
Right. So I was talking about like stability against falling in a more vague word of the sense of the word stability.
Yeah, but the first part of stability against falling is being asymptotically stable or unstable, just in the vertical. So I mean, it could be you get on a slope and then you do the other compensation, whatever it is, adding a handlebar torque or leaning the bike and get an equilibrium. The whole system is slightly more or less stable, but the first thing that happens is just adds a bias. It doesn't change the stability.
So, so let's thank again Andy for this really wonderful talk.
Thank you. It's fun. Thank you for staying late. I like the questions.